Just a reminder that it is probably a really good learning exercise for you to pause these videos, work on the questions yourself, and then check the solution rather than just watching the video straight through without trying the question first. Okay, we are going to work on the second question of the exercise set shown here, exercises on area of planar regions using horizontal slicing. So we're going to go ahead and scroll down to the second question. So the second question asks us to consider the region A bounded by the parabola x equals y squared and the line x equals 3y plus 10. So the first part, A, is to sketch this region A and find all the points of intersection. So the first thing we'll do is set up a couple of axes here. And that's not where I want my x-axis, so let's put it here. So x equals y squared is the most basic horizontal facing parabola, because the coefficient of the square, which I guess we can call a, is 1. More importantly, because it is positive, we know that the parabola faces towards the positive side of the axis, and the positive side is to the right. That is the parabola whose vertex is at the origin, so there is our curve x is equal to y squared. Now the line x is equal to 3y plus 10, we can rearrange this if we want to have it in y is equal to mx plus b form, so that we can graph it in our usual way. And if we do that, so I'm going to pull over the 10, so y is equal to x minus 10, and then I need to divide by 3, so 1/3 x minus 10/3. So I know that the y-intercept, the b, is going to be minus 10/3. So let's put that down here with not a lot of respect for scale. And I know that the slope here is 1/3. That is a positive slope. So I'm just going to go ahead and draw a line again without a whole lot of regard for scale. I'm going to change the color also of that line to make it red so that it shows up a little bit better. And there is our curve x is equal to 3y plus 10. So the region that we are looking to find the area of is the region bounded by these two curves, so we're talking about the region inside here. Now, we're asked to find the points of intersection, which means that we want to find this point and this point. Since we have the curves both in the x equals form, we can go ahead and use the comparison method, which means that we're going to set the two x values equal. In other words, x1 is equal to x2. I'm calling this guy x1 and this guy x2. So we're going to have y squared is equal to 3y plus 10, which is now just a lovely quadratic that we can solve. So we're going to bring everything over to one side. Y squared minus 3y minus 10 equals 0. And of course, I say of course because these are designed for ease of use for you, but not of course in general. This will factor. We're looking for factors here that are going to multiply to 10 and add up to minus 3, so y plus 2 and y minus 5, which is going to give us that y is minus 2 or y is plus 5. Right, so obviously this point here, I'm going to go ahead and erase in here so that I can put my, that's an x value, isn't it? So, whoops. Let's go ahead and put the y value in the correct place. So y is going to be at minus 2 here, and here the y value is going to be at 5. and y equals 5. So to find the corresponding x values, I'm obviously going to plug back in to the one of the original equations. I'll choose the simpler one. I guess that's probably this one. So I'll plug those back in, and if x is equal to y squared, then we've got minus 2 squared, which is going to give me 4. So that is the x value of this point. So our first point of this intersection is the point 4, minus 2. So these are our points of intersection. And then the last one here, or the second, x is equal to y squared. So that is going to be 5 squared, which is 25. So this is the point 25 and 5. Okay, so if we go down to question B, here we're asked to set up the integral or integrals required to calculate the area of A by horizontal slicing. And so horizontal slicing, we remember that's our rectangles drawn horizontally, and so we're looking for x as a function of y, which is how things are already set up. So we are going to go into our region and draw some rectangles just to check the boundary curves, and we see that no matter where in the region we draw rectangles, the left curve doesn't change. It's always the parabola, and the right curve doesn't change. It is always the straight line. So we are only going to need one single integral. So we want to do the integral from C to D of the right function in terms of y minus the left function in terms of y. And so our value here for C is going to be the lower value, minus 2. So we have the integral from minus 2 to the upper value, which is 5, of the rightmost function, which is the straight line. So x is equal to 3y plus 10 minus the left function, and the left function is y squared. And so there is nothing more to clean up, a very simple and straightforward integral. And so there is the answer. We're told not to evaluate, so we'll leave our answer there. If we go down to part C, now we're asked to find the integral or integrals to calculate the area of region A by vertical slicing. So rectangles drawn vertically will have a base sort of dx, which means that we want our function set up in the y is equal to f of x format. So that means we need to rearrange a little bit. Let's start with the parabola. If x is equal to y squared, then y is plus or minus the square root of x. So we've got two functions there. Let's go ahead and draw them both in. So in orange, I'm going to draw y is equal to the root of x, the positive root of x. And in blue, I will draw y is equal to minus the root of x. So let me go ahead and get rid of the label in black. Now for the straight line, x is equal to 3y plus 10. A little rearranging here is going to bring over, so 3y is equal to x minus 10, and I'll divide both sides by 3. X minus 10 over 3 is the curve in red, so let's go ahead and change that label as well. So y is x minus 10 over 3. And then if we imagine drawing our rectangles vertically this time, we see that rectangles drawn over here are going to go from the blue on the bottom to the orange on the top, whereas rectangles drawn over here are going to go from the red on the bottom to the orange on the top, which means that we need to split our region in two. We're going to have the first region from 0 to 4, and the second region from 4 to 25. So this time we're doing the integral from a to b of the top minus the bottom, because we're doing vertical slicing. So there's the general formula. We need to apply this twice, obviously, because we've got two integrals. So we're talking about the integral, the first one, from 0 to 4, we said. The top is the positive square root of x minus the bottom function, which is x minus 10 over 3. Add to that the integral for the area of the second region, so the region we said from 4 to 25. The top function is still the root function. Oh, no, I have screwed that up, haven't I? I have screwed that up, so let's get rid of this. The function in the first region, the bottom function, is the function in blue minus root x. And now the second region from 4 to 25, that's what I'd written previously. So square root of x minus x minus 10 over 3 dx. And then just a little cleaning up that we can do here, so this will become 2 times the integral from 0 to 4 of root x dx, plus, and this one, there's not a lot that we can do, but why don't we separate things a little bit as if we would need to integrate, although we don't, because the question says do not evaluate, but I can separate and bring through the minus sign, and there is the final answer for part C. So which of B or C would be easier to evaluate? Well, it's the same as the first question on this exercise sheet. It's going to be B is easier, and for the same reasons as well, right? There's only one integral instead of two to evaluate, and the integral is actually an easier integral. It's polynomial functions instead of root functions. Root functions are not terribly hard, but the polynomial is maybe even that much easier.